Hello, dear colleagues. It's an honor to present our work today at the 8th International Workshop on Computer Modeling and Intelligent Systems. On behalf of the Limos Laboratory from the Computer Science Department at the University Mohammed Bouguera, Boumerdès, Algeria, I am delighted to share our collective research on comparative evaluation of StyleGAN3 based augmentation strategies for enhanced medical image classification. First, we will begin with an introduction and problem statement. Next, we will review the literature. After that, we will discuss the methods used in our study. Then we will examine the obtained results. Finally, the conclusion. In the field of machine learning, the quality and the quantity of data play a crucial role in the effectiveness of models, especially in sensitive sectors like medicine. However, a recurring issue in medical datasets is class imbalance, where certain categories of images, such as those related to rare pathologies, are significantly underrepresented. This situation can lead to biases in classification models, reducing their performance and ability to generalize effectively. Traditional data augmentation methods do not sufficiently correct this imbalance. It is in this context that data augmentation techniques and generative models such as GANs play a key role by offering new opportunities to generate synthetic images and balanced datasets. Before continuing, I will show you two images. Can you guess which one is real and which one is synthetic? In reality, both images were generated by a model called StyleGAN3. Now, moving on to the objective of this project. Our goal is to generate synthetic images like this for minority classes using GANs, particularly StyleGAN3, in order to improve the performance of classification models. We conducted a literature review to analyze existing works on synthetic image generation using GANs for the COVID-19 and HAM 10,000 datasets. Article by Abdul Wahab and Sharmila, both studies focused on the COVID-19 radiography and COVID chest X-ray datasets. In the first article, they developed a model called COVID-GAN based on the auxiliary classifier GAN, AC-GAN, to generate images of size 112 pixels. In the second article, they combined DC-GAN with CNNs to generate images of size 256 pixels. For the HAM 10,000 dataset, in the article by Ahmed B. they combined VAE's variation autoencoders with two generative models to generate images. In the article by Kinshan, they proposed a model called STGAN to generate images of size 256 pixels. Finally, the article by Guillaume they developed the StyleGAN2 ADA approach for generating eye challenge fundus eye images of size 224 pixels. In conclusion, these studies highlight the diversity of approaches and GAN architecture used to address classification problems in critical model domains, and they served as a foundation to guide our own work. GAN is a subcategory of generative models, first introduced by Goodflow in 2014. The generator and discriminator are two neural networks and essential elements in the GANs. These two networks collaborate in an opposite but complementary way, competing against each other. The generator takes a random vector input and produces a synthetic image, which will be taken initially by the discriminator, which tries to determine if this image is real or synthetic. The generator is trained to deceive the discriminator by generating data that seems real. On the other hand, the discriminator is trained not to be misled and to distinguish the real data from generated data. This competition leads to a gradual improvement of both networks. The generator is becoming more adept at producing realistic data, while the discriminator is refining its ability to detect fakes. The following function describes the interaction between the generator and the discriminator as part of the training. Let's now move on the functioning of StyleGAN3, which relies on a series of advanced processes that enable the generation of high-quality images while solving the problem of aliasing. It all starts with the sampling of our latent vector. This vector contains the necessary information to generate an image. This vector is then transformed by a mapping network into a new vector W, which is better organized to control the style of the image. Next, it passes through Fourier features, which capture spatial frequencies, making transformation smoother and more natural. This prevents detail from being fixed to a specific position in the image. Then the data passes through a 1x1 convolution, which adjusts the features for the progressive generation of the image through a series of layered blocks L0 to L13, where each block refines the details and increasing resolution. This is achieved using modulation and demodulation. At the end of the architecture, the information passes through a 2RGB layer, which converts the data into RGB pixels, thus producing the final high-resolution image. To stabilize the training, an exponential moving average (EMMA) technique is used, smoothing the model's ways to ensure stable and artifact-free image generation. We worked on two datasets, the COVID-19 radiography and the HAM-10,000 dataset. The COVID-19 radiography dataset contains 16,913 training images and 4,235 test images, divided into four classes: normal, viral pneumonia, COVID-19, and lung opacity. The HAM-10,000 dataset consists of 8,010 training images and 2,005 test images. It's used for skin disease classification and includes 7 classes such as melanoma, NV, BCC, and others. The training of StyleGAN3 was conducted separately for each minority class in the COVID-19 and HAM-10,000 datasets to ensure that each model learned the specific characteristics of each class, ensuring that only the images from the training set were used to prevent data leakage into the test set. The pre-processing of the data included cleaning the dataset, resizing the images to 256 pixels, cropping, converting the images into tensors, and normalization. In the context of our project, we explored different data augmentation approaches. In this first approach, we used traditional augmentation techniques. These techniques include applying basic operations such as rotation, flipping, and other transformations to the images during the training of the classifier. This method artificially increases the size of the dataset by slightly modifying the images, allowing CNN models to generalize better. In this next approach, targeted augmentation for balancing, we added a balancing mechanism using traditional techniques such as rotation, scaling, contrast adjustments to generate new synthetic samples. These generated images are added to the minority classes, aiming to create a new balanced dataset. This balanced dataset was then used to train the classification models. For approach 3, StyleGAN3 based augmentation with batch injection, where StyleGAN3 is used to generate synthetic images instead of pre-generating a fixed dataset. The synthetic images are injected in mini batches directly into the training process, ensuring dynamic augmentation during model learning. In this final approach, called the hybrid StyleGAN3 augmentation and traditional balancing, we combined image generation using StyleGAN3 with traditional augmentation techniques. First, we augmented the minority classes by a certain percentage, 10%, 20%, 30%, or 40%, using synthetic image generated by the StyleGAN3 generator. Then, we balanced these minority classes using traditional data augmentation techniques, resulting in a new dataset that was used to train the CNN models. The following table presents a comparison of the performance of the classification models ResNet 50 and Inception-V3 on the two datasets COVID-19 and HAM 10,000, using the four previously explained approaches. The table summarizes these results in terms of accuracy, recall, F1 score, and finally precision. For the COVID-19 radiography dataset, approach 4, which includes 30% increase in generated data, proved to be the most effective. It achieved an accuracy of 95.96% for the Inception V3 model and 94.49% for the ResNet 50, outperforming all other test approaches. In the HAM 10,000 dataset, approach 4 also delivered the best results, especially for Inception V3, which reached an accuracy of 86.43%. We present the experimental results comparing the proposed method StyleGAN3 plus balancing approach with previous studies on COVID-19 radiography. The results show that the proposed method achieves 95.96% accuracy, outperforming the COVID-GAN 95% and DC-GAN-CNN 94.80 to 98.60%, while significantly improving upon the baseline without augmentation 85.11%. On the HAM 10,000 dataset, compared to existing works, our approach, which combines StyleGAN3 and balancing techniques, achieves an accuracy of 86.43%. This places it among the competitive methods, significantly improving upon the baseline without augmentation 73.5% and approaching the performance of advanced methods like TED-GAN 82% and ST-GAN 98.23%. While our approach does not surpass StyleGAN, it demonstrates strong performance, particularly in handling minority classes, confirming its effectiveness in improving classification models for skin lesion datasets. The following images are synthetic images generated by StyleGAN3. In conclusion, the use of StyleGAN3 with class balancing brings significantly improvements for minority classes, while offering an effective complement to traditional methods to enhance data diversity. Our experiments showed that while StyleGAN generated images are realistic and useful for data augmentation, they do not outperform traditional methods. Challenges remain in achieving sufficient diversity and realism, especially given the complexity and variability of medical images. However, the study shows that GANs have potential for improving medical datasets, and optimizing architecture like ResNet 50 and Inception V3 could enhance model robustness. Further research should be aimed at hybrid methods, combining GANs with other generation techniques, and combining imbalanced handling techniques, such as undersampling the majority classes through pruning while simultaneously oversampling the minority classes. Thank you for your attention.